In week 3, we set up an initial rigid body sim, and now we can go ahead and add our constraints to that. But the constraints that we generated during our fracture process only exist within each individual piece that we fractured. Now we fractured all the different sections of the geometry in a loop, so this will only generate constraints within each section. So for example, this floor section here only has constraints within itself, and it has no constraints between it and other nearby objects. So the first thing we'll have to do is add constraints between the different sections. So we'll go back to the object level and we'll create a new section for that. I'll just call this week 4 constraints between sections. And then we can dive inside and we'll object merge in our cached optimized fracture. So we'll pull that in from object, week 3, fracture optimize, out fractured. And in order to do anything with this, as we've seen before, we'll have to use an RBD unpack node to separate out the fractures and constraints and proxies. And we could use either the fracture geometry or the proxies to generate these extra constraints from, and the proxies are generally more lightweight, so I'm going to use those for as much of the processing as I can. So I'll start by dropping in a null next to that RBD unpack, and I'll just call this proxies. And the technique that I'm going to use to generate constraints between the sections is a point lookup to find the nearby packed pieces, and since we're going to be operating on points, we'll need to promote our name and our original name from prims down to the packed points. So we'll start by dropping in that attribute promote and set the original class to primitive, and then select both the name and name orig. And now that we have our name and name orig pushed down to the points, we can just get rid of all the primitives since we're just going to operate on the points alone. So you can just drop in an add node and select the delete geometry but keep the points option. And then to visualize all the different sections that we'll be working with, I'm going to add a random color based on that name orig attribute. So connect up your color node, set it to random from attribute, and the attribute is just going to be name orig. Now we're going to use a detail wrangle to generate the constraints between those sections. So to create that, just drop in a normal attribute wrangle and connect that to the color, and under this run over parameter, just select detail. You can see that says it's running only once. On the point or primitive wrangles, that would run the Vex code for every single point and primitive in a loop, whereas this detail just runs once on our overall input. However, in the actual Vex code that we're going to enter here, we're running a loop over all of those points, and then in that loop we're looking up the neighbors and checking to see if they're in the same section or not. In this Vex code, I also have a couple local parameter lookups to parameters called constraint distance and max connections, but you'll notice those parameters don't actually exist on this wrangle node yet. And there's a really convenient feature built into these wrangle nodes. Anytime you type in chf for floats or chi for integers, there's also a version for ramps and strings, you can then hit this little button here and it'll generate any of those missing parameters for you. Just one word of warning, these names here have to be valid internal Houdini parameter names, so they can't have any spaces or anything in them. And once you generate those parameters, you can go to your edit parameter interface and move those to the top if you'd like. I just prefer to have mine up there for easier access. And you can just hit apply and accept. And these controls make it a bit more user-friendly to control the distance that each point is looking for neighboring pieces, and to control the maximum number of generated constraints on each point. And you can play around with these values if you'd like, but in this case I'm using a constraint distance of 3 and max connections of 10. Also, don't worry if you're not much of a programmer and this Vex code looks intimidating to you. You can always save this snippet for later and then just control the effect with this max connection setting and the constraint distance, you shouldn't really need to mess with the actual code very much. And the way that this snippet here works is it starts by defining some variables for our array of near points and to store the current point in our loop. And it sets up some string variables to store the section A and section B for each point comparison. Now the endpoints will look up the number of points in our input, and that for loop will just run an iteration for each number within that point number range. And now for each of those point numbers, I'm doing a pgfind lookup on our input geometry, and I'm getting the current point number's position and searching for other points within the distance defined by our parameter up here, and with the maximum number of connections defined by the other parameter here. And this final argument is a size value to optimize the lookup of the pgfind. If you ever want to find out more information about any of these functions, you can just click on it and hit F1, and that'll bring up that exact function in the help doc here, and it'll describe all of the various inputs to those functions. And now this pgfind function will return a list of points that are near the point that we're checking, and for each of those returned points, we'll compare that to the point we're running this loop on, and it just compares the name orig for each of those nearby points to the name orig of the current point we're checking. And if those are not equal to each other, so they're in different sections, then we'll use this add prim function to create a polyline between them. The output also contains all of the stray points that we didn't need to generate any constraints for, but we can clean those up with a clean node. Now on that clean node, make sure to turn off remove degenerate primitives, and you can leave on that unused points option, and that will clean up all of those points that aren't part of a primitive line. I also like to add an extra attribute to these generated lines here so that we can differentiate the constraints between sections from the other constraints in our setup. So you can just add in a primitive wrangle. I'll call it between sections attribute and connect the clean to that. And in this vex, I'll just type I at between underscore sections equals 1. It's also good to have a rest length attribute on your constraints because some constraint types need that information. So you can add that with a measure, and we'll set that measure to perimeter. And instead of using that default attribute name of perimeter, we're going to call this rest length. And then with those attributes sorted, we can drop in an attribute delete to clean up the ones that we don't need. In this case, we don't need the name orig on our constraints, and under the primitive attribute, we don't need this bbox size or the path. And now we can merge those constraints with the original constraints that we already had from the fracture process. If you want to keep this visual indicator between them, you could set a color on the original constraints as well. Maybe I'll just set it to a flat gray color and connect our constraints to that, and we'll merge our new constraints with the old ones. And now that we've added these new constraints, we'll need to pack our destruction asset back up, so we'll drop in a new RBD pack, connect our constraints to the second input, we'll grab our fracture from the first input, and maybe pull that wire to the side just to make our network a bit more clear, connect the proxies to the unpack proxies as well, and maybe just rearrange that network for clarity like so. And then we'll add a null at the end so that we can refer to this elsewhere in the scene, and I'll call this out with extra constraints. You could cache this out to disk if you'd like to, but we're going to do some more work on our constraints and set up some clumping for this, so I'm just going to leave this live in the scene, and I'm not going to bother setting up a separate cache for this step.